Good, thanks. Pleasure to be here. Thanks, Bob, for warming up the crowd. Uh, so I'm going to talk a bit on the side of deepfake detection, um, just to in case someone doesn't know how easy this is. I have never been skydiving. That's a picture of me in the lower left, and I have yet to climb Mount Everest. Probably never will. That's a picture of me at base camp. There are currently in the community several different types of deepfakes, different tools to create them, and we're seeing the emergence of hybrid deepfakes. So instead of just one type, folks are putting multiple types together, which tends to add credibility to whatever story is trying to be told. On the top left-hand side there is Pope Francis in a puffy white coat. Not a true picture, made the rounds of the internet quite a while ago as one of the early image deepfakes. The block of text below was below the Pope there was entirely generated by an AI engine. And then the final piece on the lower left about the flood with the text that looks like a news report and the picture that appears to be the White House with flooding in front of it is also entirely false. So a human used a text prompt, White House floods during DC rainstorm on August 9th. ChatGPT spit out the story that's in light blue right below that. And then the Midjourney image generation tool created a very realistic looking image of that event happening. So you can imagine this showing up on the news feed and appearing quite credible. It's not just the text, but it has a picture to go with it that matches the text that's there. In the upper right is the video. I won't play it, but it's a video of dogs playing in the snow, generated from whole cloth. There was no original video that was modified. No one's face was swapped out. The prompter provided yellow lab puppies playing in the snow, and this video gets created out of that tool. This was the Sora AI tool. Similarly, or not similarly, in a different vein, there are several tools out there that will, in real time, take one person's voice and alter it to give it the feel and sound of another person's voice, for which the creators have some number of samples. This matters quite a bit in the public domain. So actors, for which we have hours and hours of movie footage, public figures, for which we have hours and hours of media coverage, including audio and video. So the particular sample here is a gentleman who has it's kind of a run-of-the-mill accent. And as he's talking into the microphone in this video, he sounds very much like Gandalf the Wizard from the Lord of the Rings trilogy. That's a picture of him on the right in real time. And this is a piece of the technology that we're seeing emerge in something called vishing. That's phishing with a V for Victor, for voice phishing. So an attacker can type a script or talk in real time, even with an accent, and have their voice translated into someone else's voice. You can imagine if someone had enough recordings of a family member and you got a call and said, hey, this is your son, daughter, spouse, whoever, and it sounded like them, you're very likely to go along with whatever the scam is at that point. Phishing was used by some attackers who hit the casino in Maryland a while back, the MGM casino. They pretended to be IT folks. They did not have good English skills. They were typing in real time at the keyboard, and it was being turned into voice audio output as they were talking to the help desk and trying to talk their way past the security measures. Probably the most, the oldest in all these categories is the image stuff. That's, you do very funny stuff with that, very damaging stuff as well. In the lower right is what has emerged as kind of the state of practice for deepfakes, and that is putting a video start with a raw video, alter the video to be someone famous, for example, add in AI generated audio to go with that video. And now you have a video clip with sound of the person telling you something. The example in the lower right here is Taylor Swift telling all of her fans that if they go to a particular URL, they can get a free set of cookware. Entirely false. Taylor Swift has nothing to do with that. Taylor Swift never said any of the things in the video, and this isn't even a very particularly good quality one, but you can see where a potential victim would fall for this. Kind of harmless if you go to a website looking for free cookware, but obviously there are a lot of more dangerous tricks that could be perpetrated this way. All right, so kind of on to detection. I'm going to talk about detection in kind of 3 levels, but I'm going to go through the first 2 very quickly. This is kind of common knowledge stuff, and spend a little more time on the technical analysis piece at the end of this. So right out of the gate, we've got a teddy bear at the Masters wearing a green suit. We have some dogs and grizzly bears playing poker in the upper right. So the first thing is, does the image or the video or the sound, does it pass the sniff test? Is this a possible thing that could realistically happen? Teddy bears don't play golf as far as I know. They certainly don't wear that kind of outfit if they did play golf. Do dogs and bears play poker? Probably not. So imagine now that your image has passed the sniff test. So maybe you think a lot of me and my physical conditioning, and you're like, well, maybe Jim really did climb Mount Everest. So when is he claiming to have climbed it? Can I prove that he was actually somewhere else when he claimed to climb it? So this is going to external sources to verify what's in the potential deep fake. For example, if I was teaching a class and there's a video recording of a class or giving a talk at the time that I claimed to be in Nepal climbing Mount Everest, then it's obviously fake. Can I provide any receipts to support that I actually did it? In the case of Everest, there's an online list of everyone who has ever summited Everest. And so if you go in there and you search for Jones, you'll find a dozen or 15 different Joneses, none of them Jim or James Jones. So if I did climb Everest, I snuck up there and nobody noticed that I was there. The third in this kind of first level screening is to look for things that just aren't right. And the classic example in early AI generated videos was hands. People's hands are actually really hard for the AI to get right. And there are a couple examples where people have fingers about a foot long hanging from their hand. People have 6 fingers, they have extra thumbs, the fingers overlap and they're in the wrong place. I don't think we as humans appreciate how complicated our hands and our hand movements are. The AI doesn't get that right much now out of the gate. There are ways to manipulate it later, but we'll talk about how we detect that stuff. So in looking for anomalies, besides hands, faces are one of the other things that are very hard for the AI to get quite right. Do people blink? Do they, is their face moving smoothly and transitioning from one expression to the next? On the fake video with audio side, or just an audio deep fake, does the audio match who we think is talking? So you can imagine a very high-pitched woman's voice and a big guy with a beard, probably not legitimate. Most deep fakes are meant to try to fool us, so they're going to try to match the voice to the character that we're seeing talking. But is the audio in sync with the lips? There's some really nice detection work being done at the University at Buffalo on essentially focusing in on the lips and the audio that's happening. So they built this library of what a person's lips look like when they're making a certain sound, and then does the video of those lips match the sound that's being played in the audio? Obviously, real audio can get off by some amount of time in real life, but if we re-register the audio to the lips, then we can look very carefully at, are the sounds matching what the lips are doing. Also with audio, Are there unexpected gaps or delays? Is the pacing of the person's speech appropriate for what we would expect them to say? And interestingly, if it's somebody we potentially know, we can look for mispronunciations. So if I'm speaking to someone and I know they're fluent in French and they mispronounce some French phrase, I'm going to be very suspicious that that's not actually the person. By the same token, if I'm talking to my wife and she pronounces something in French perfectly, I know better. I know she doesn't know French and she's not going to know how to say something like that. Similarly, there are things that people say, mannerisms in their speech that we learn to pick up on over time. So if you know the party well, it's much harder to fool them with a deep fake. There's some suggestions that with family members, we should set up special words or phrases that we can identify or verify, authenticate ourselves to someone else. So if my son calls me and says, "Hey, Dad, I'm in a crisis and I need you to wire me some money," I'm going to say, "What's the code word?" And he's going to give me the code word, and then I'll know it probably really is him versus not. If somebody trying to fake him. And then lastly, in this set of anomalies we look for, lighting is one of the hardest things for AI to get right. It's not that we can't model the physics of lighting, it's that being able to do it in complex scenes with movement and shadows and objects moving in front of other objects in real time is very hard for an AI engine to get right. So a lot of the analysis, the detection techniques, and a couple that we'll talk about in a few minutes, have to do with lighting and shadows and how things look in an image or a video. If you're trying to assess an image for a potential deep fake, then all of these make perfect sense. If you're trying to analyze a video, it's actually much harder for humans to do this with video. So if you don't know, most of your brain is spent on visual processing while your eyes are open. And so your brain is already really busy processing all this stuff that's coming in, and it is very prone to take shortcuts. And so your brain will skip over the fact that the mouth isn't moving quite right, or that there was a transition where the mouth moved and none of the rest of the face moved from one side to the other and things like that. Your brain is very good at ignoring those. So if we're trying to look at a video and determine whether it's fake or not, one of the, not going to say easiest, but most straightforward things to do is to turn it into a frame-by-frame representation of the video, especially if you have a window of time about which you're suspicious, like when the person said the thing that you can't believe they said, narrow it down to that. And even at 30 frames per second, if you're talking about a few seconds, it's 100 or 200 maybe frames of video, now turned into still images. And there's a tool called FFmpeg, which is free, which will turn a video into individual frames. Now we can apply all these image analytic techniques to the individual frames and help hopefully be able to see when something is faked. So now kind of onto the technical analysis piece of this. The first thing we're going to start with is what I would call classic digital forensics, the stuff that, as Bob mentioned, we've been doing for years. So we're going to look at the source of a piece of content, right? If it came in email has headers with it that tells me who sent that message originally and the systems through which it hopped with some reliability. It's not cryptographically secured, so I can't be certain. But I'm going to look at those headers and say, okay, A, do the headers match where I think it came from? And B, where do the headers tell me it came from? And do I trust that source? To one of Bob's other points, if the content is cryptographically signed, then I have a little more assurance that it actually came from an entity that either knew that passphrase or was the actual entity I think it was. Same thing with websites. We can track down the IP address of a website. We can track down the ownership of the website. We can track down who supposedly created that content that we've received. Second thing, for some images, we can compare them to known images. So if I have one that I think has been slightly altered, but the image itself is in the public domain, I can go out and compare those two images. And if they look similar but not quite the same to me, I can prove that mathematically. And if they look the same to me, but I suspect they aren't, I can also check that mathematically down to individual bytes and bits. And so if I know they're different, then I'm suspicious of the source. Also because many deep fakes take a raw image that is left mostly intact, and they simply paste one person's face on over the other person's face. There's a very limited amount of the image that's changed. And so what I can do is look for the stuff that's not the person's face in an image search. And if I find a match there, I go, oh, there's the original picture with person A. I got sent that picture with person B's face in it. I know obviously that it's been altered. In the case of digital content like images, video, and audio sound recordings, those digital files have metadata attached to them. And among other things, that metadata has information about the time the image, the file was created, last accessed, and modified. It may have location data in the form of GPS data, and it may have information about the devices that were used to originally create the content. Also, if particular software was used to modify the content, that gets captured in the metadata. All of these are modifiable. So a sophisticated operator is not going to let this stuff slip through. But if you take the picture of Jim Jones at Mount Everest and we look at the properties of that, there is no camera information. So it's highly suspicious that a picture got taken of me at Mount Everest without using a camera of some type. That's exactly what happened. It got created by an AI generation tool. If we look at the picture in the middle of the dog, that was taken with an iPhone in this case, at the bottom you see we get the iPhone, we get the model number, we get the settings of the camera in the iPhone, we get the GPS data in the middle there. The phone has a GPS chip, it knows where it is, and if you don't tell it not to, it's going to stuff the GPS data into the picture metadata, and we get some timestamps about when the picture was actually taken. Same thing with the picture on the right. We take it with a different kind of camera, but we now see the camera. So if we know that a picture was taken with a particular device, and then we get something supposedly taken with that device, and the device information doesn't match or is missing, then we're immediately suspicious. So those are kind of the class techniques. Moving on to some of the more advanced stuff that's being worked on now, and I've got a few of these to go through. We'll make sure that we have plenty of time for Q&A after this, or during. Feel free to ask as well. So one of the first things we do is basically measure the level of compression of the contents of an image. And one of the ways to do this is called error level analysis. And you can think mentally that ELA, error level analysis, is a measure of the compression of the pieces of a picture. So the original image is in the upper left. The error level analysis output is in the upper right. And you can see that it's fairly uniform. There aren't a lot of hot and cold spots that don't correspond with darker white spots in the original image. It's not that the ELA should be flat, all white or gray or black. It's that it should roughly match the picture that's there. In the lower left, a dinosaur, a T-Rex, has been added in the middle of the kind of middle right of the picture there. And that Introduction to Network Security book and the one next to it about Ubuntu have been repeated multiple times in the bookshelf. That they're each in there one time in the original picture and then 3 times total in the picture in the lower left. So when we do the error level analysis of that modified image, you see that the dinosaur and those 2 blocks of books show, 2 of the 3 blocks of books, show as higher levels of error. And what's happening is the compression is affecting the error level in a consistent manner as the picture gets compressed and compressed. As the picture gets modified and something gets added like a dinosaur, that dinosaur is at a different level of compression than the original image, and so it stands out. What the image in the lower right is saying is the compression level for this thing that's shaped like a T-Rex and 2 of these 3 chunks of books in the kind of left, middle, and left side of the picture there, the compression is different. And that is a dead giveaway of manipulation of the image after it was originally taken. Another type of analysis says I'm going to look at neighboring pixels and I'm going to measure the distance, meaning how different are those neighboring pixels. So the original pictures in the potentially modified pictures in the left, and the measurement of average distance is in that picture on the right. Some of these things we expect. Notice how the picture on the left has the vertical slats of the barn there, and in the picture on the right, the ADMP picture, we still see those planks and the groove between them. And that's because there is a significant difference in color between the boards and the spaces between the boards. That's what we expect. But you'll also notice that most of the wall and the lines between the slats looks kind of the same. It's not uniform, but it looks kind of the same. But if we look closely at the rider, and specifically the saddle pad that she's got on the horse, so the kind of olive green saddle pad that sits between the saddle and the horse there, you'll notice that the part behind her is fairly uniform, but the part that's in front of her left leg there, it's not that black line, that's part of the saddle. It's that green swath in front of her left knee that in the picture on the right shows up as this kind of pink color. And what that's saying is that's not the same as the part that's behind her leg. And for consistent lighting, a picture like this, consistent distance to the two parts of the saddle pad should look the same in front of her leg as it does behind. And the fact that it doesn't says the image has been manipulated in one place or another. And with this type of analysis, this would suggest that the part in front of her left leg has been manipulated in some way. Similarly, if you'll notice most of the body of the horse's flanks on the right side and the horse's neck is this just kind of dark, almost black uniform color. But when you look at the horse's legs, they light up. And they light up because they too have been manipulated. So the legs, which in the left-hand picture are the same color as the rest of the body of the horse, should look the same in the ADMP picture, but they don't. And so that says something, probably smoothing in this case, was done in the horse's legs, and probably something in front of the rider's left knee there. Another way to look at images is something called luminance gradient analysis, which is just a nice way of saying how light changes in a picture and how light is reflected off of the objects in the picture. The example on the left is called a bump map, which is designed to reflect the 3D nature of things in a picture and how light bounces off of three-dimensional things. And the takeaway from this is you'll see there's a person's lower legs and boots, 2 feet in the lower right-hand part of the picture behind the person that's voting. And in the bottom picture where the luminescence or luminance has the difference in lighting from one pixel to the next has been measured, you see that person's shoes back there light up kind of bright red, almost pink and white. And what that suggests is that the picture taken of those feet were under different lighting conditions than the rest of the picture, which has this other kind of light or not so sharp pattern to it. And in this case, those legs and feet were added to the picture after it was originally taken to make it appear that someone was voting behind this person. The picture on the right is a little bit different, but it still uses this luminance gradient analysis to call out where parts of this picture have been modified. The most noticeable is on the woman's right arm. It's in the white circles in the lower right picture. It's the leftmost circle. Her right arm, where her tricep is, has that big black swath at the bottom of it. And that's a dead giveaway that that's been modified. Don't know what the modification was, but something has happened on that lower part of her right tricep. The shading on her abdomen is irregular, which suggests that's been touched up. The background has been blurred, which isn't a dead giveaway. But then the other dead giveaway of manipulation after this picture was taken is her face. And what you'll notice is the right side of her face has mostly red and the left side has this green. That says that the lighting's not the same. She is staring straight at the camera, straight at the light. It's a professional picture, yet her skin is not reflecting the light in the same way from one side of her face to the other. And what probably happened here is some type of skin smoothing to make the picture appear more uniform, her face or her skin appear more uniform. Got just a couple more. JP will probably go till about 4:20 or so if that works out, and give us some time for Q&A.
Yes, that's fine, and for Matt also. Thank you, Jen.
Yeah, for Matt, exactly. Yes, thank you. Yeah, sorry, Matt. Yep. So a common technique when trying to, in particular, hide something in a picture or add something to it is to copy one part of the picture to another. So for example, if there's an airplane and you don't want the airplane to be in the picture, we just take a chunk of sky, copy it, paste it over the airplane. In this picture on the left, those shoes that are highlighted have been copied and pasted either from one place and then replicated in another, or entirely introduced from outside. Most likely from this picture, one is copied from the other. And the way to detect this is to do a similarity analysis between different pixels in the picture. So it's very unlikely that different parts of a picture have exactly the same pixel profile. And what we have here is two sets of shoes that are exactly the same. It's easy to see once it's highlighted, but if you just glanced at it, you wouldn't notice. So the analysis shows up in the right-hand picture here. Those blue blocks are the shoes. You'll also notice that the sky is riddled with pixels that are the same. Okay, it's a clear blue, almost uniform sky that's going to happen. So this almost certainly false positives in the case of this analysis, but it's also possible there was something up there that someone wanted to hide and they just copied a piece of the picture and slid it over here over another. Same thing for those two orange blocks and the two kind of light yellow tan blocks. Those are probably just random matches of color because it's the water that looks the same, but they could also be hiding something. And then moving kind of briefly into video, this is very recent work, the links there, and I've got some references as well at the end. This is work that's using a machine learning model, a fairly sophisticated one, to analyze the transitions in the frames of a video. So in other words, going from one frame to the next, are the changes reasonable based on a training set of normal video unaltered, and based on a training set of altered video, what do those alterations look like? So this tool will take a whole video and will highlight the frames that appear to represent modified transitions. In the three videos up here, three video clips, it's the red boxes around the individual frames that suggest they've been modified. They do not represent a natural transition from the frame before. There's something unusual in the model. And the researchers here got high 90s type of accuracy when doing that. Last thing I wanted to share with you is an online tool. So the last one is a tool, but it's very research-based, usable, but requires a little bit of work. This is an online tool that if you know how to upload a picture, you know how to use this tool. So the Deepfakeometer is out of the folks at the University of Buffalo. I uploaded a picture of me at Mount Everest, asked to run all of their algorithms, current and past, on it. Those are the gray boxes on the right there. Submitted it. Takes about 3 to 5 minutes to process all of those. And in the lower left are the results. And what you'll notice is one of the algorithms, the GLFF, pegged at 100%. Yep, that's definitely a fake picture. A lot of them said no. But all that means is that that algorithm did not see the things that it's looking for to detect a fake picture. One of the limitations of many algorithms is they look for a particular thing, and if they don't find it, they say, I can't say it's fake. So what's emerging are tools like this that will run multiple tools against your image or your video or your audio, which this tool works on all three of those types of input, and then spit out an answer for each of the tools. And as a user, I'm just looking for one or more of those to have a hit. And then I'm suspicious and I can start digging into what did that tool look for? Now can I go find it by hand? So I want to make sure I leave plenty of time. JP, this will be in the recording, obviously. These are just a handful of references. There are thousands and thousands of good references on this deepfake detection work. But I'll also happy to share the